today that obeys a certain recurrence relation. We want to show that if the first term in the sequence is not a perfect square, we're right here. I'll just write it down for you. This is a number theory question, so all the quantities involved are integers. But just for emphasis, if the very first term in this sequence is not a perfect square, we want to show that the entire sequence cannot contain a perfect square, meaning there's not a single perfect square in the entire sequence for all n, okay? Now we're going to start out with a result here that's not surprisingly useful, I guess, although you would know to use modulo 4, I think. Now, modulo 4 just means what remainder do you get upon division by 4, like 5 mod 4 is 1, 6 mod 4 is 2. So it's the number you get after you divide the given number by 4. Now, a very well-known result is that a perfect square is equal to 0 or 1 mod 4. I could use congruence. I'm just saying modulo, though. So a perfect square, this is very, very easy to prove. I won't prove it for you. But what I'm going to do is work with the contrapositive. So let's call this the implication A implies B, right? You guys who've taken logic, or just, I guess you want to call this common sense if you want, an implication is equivalent to its contrapositive, which is exactly what this is. You either can be congruent to 0, 1, 2, or 3. So the contrapositive is represented by this green statement here, and it would be in the form not B. Let me make that a B, folks. Okay, that needs to be a B right here. Not B. And what I'm writing down here, y'all, is called the contrapositive, and it's logically equivalent to the original implication in a truth table sort of way. So we got this. Okay. Now, to me, this is more explicit as far as what we're trying to do. We're saying it's not a perfect square. Any integer is not a perfect square if it's congruent to 2 or 3. Okay, if it leaves a remainder of 2 or 3 mod 4. All right, and that's the contrapositive of this very well-known result right here. So let's move along. And so it makes quite a bit of sense. Now notice right off the bat here, 67 is congruent to 3 mod 4. Okay, 67 minus 3 is 64, and 64 is certainly divisible by 4. And so all these computations are very, very easy to perform. A at n, if a sub n is congruent to 0, then a sub n plus 1 is congruent to 3. That follows immediately from this statement, and the rest of these computations are very easy. This would be 68. If you worked out this would come out to be 68, and 68 is congruent to 0 mod 4. And so I won't go through all of these, but anyway, what we see here is a nice result. We see that everything except for 1 gets sent to 3, 3, or 2, right? Remember that if you're congruent to 3 or 2, you're not a perfect square. All right, so remember our original term, our original initial term in the sequence is not a perfect square. So what does this imply? This implies that a sub 2 would be congruent to 3 or 2, right? Okay, again, that's what these computations show us. A sub 1 is not a perfect square, and so according to this right here, that means a sub 2 would have to be congruent to 3 or 2 based on these two results here. Okay, and again, y'all do the individual computations if you don't believe this, but this is just a direct substitution back into the original. If you substituted 2 in here, for example, you would get 8 plus 67 is 75, which is congruent to 3 modulo 4, right? So you see, A1 not a perfect square means the successor must be congruent to 3 or 2, and so on. This would imply that A sub 3 would also be congruent to 3 or 2. And again, it's understood we're doing mod 4 here. Y'all, and you see this would just go on ad infinitum, right? So what we have here is that a sub n is not a perfect square for all n. Okay, again, now this isn't super formal, but once you get the ball rolling here, each successor, if the original term is not a perfect square, that means the successor has to be 3 or 2 by these computations here. And so we have a sub n is not a perfect square for all n greater than or equal to 1. So some of you may not think that's a very surprising result, but this was very similar to a competition result. Gosh, long ago, I can't remember the name of the competition. It was back in 1999. But anyway, we've proved what we set out to prove. Thank you for viewing.